Hello everyone, I'm Liangxian, a postgraduate from University of Science and Technology of China. We're delighted to participate in this challenge and give a speech. Today we'll be discussing our method G2D, GAN-based GDLnet for 60 object pose estimation. In recent years, with the advancement of deep neural networks, object pose estimation has become a hot research topic, and existing research has demonstrated the great potential of 60 pose estimation using CNN networks. In Behave Challenge, our task is to estimate the object pose directly from a single RGB image. In our method, we model the problem as first predicting the NOSS normalized object coordinate space map from a single RGB image, and then solve object pose using a learnable regression model. It is worth noting that we input the cropped RGB images and output their corresponding OSS maps. Therefore, an additional transformation needs to be applied to the 2D pixels to obtain the final 2D to 3D correspondence. To address these challenges, we propose a GAN-based GDLnet network. The pipeline of our approach is as follows. We first encode the input RGB images into intermediate geometric features, such as 2D to 3D correspondences and surface region attention. These features are then fed into a learnable patch PNP model, which directly outputs the object pose. The 3D models mentioned here are used to render corresponding OSS maps and surface attention maps on the training set, which serve as additional supervision signals to guide the training of the network. We successfully address the issue of object symmetry by clustering the point clouds of the object into different surface patches in surface attention maps. Furthermore, we employ a generator discriminator network to address the challenge of occlusion, which will be detailed later. In addition to pre-rendered OSS map and surface attention map, we employ the following data pre-processing methods. Firstly, based on given mask, we use OpenCV to obtain the maximum bounding box of each object and employ an average strategy to determine the position of the center point. To include more global context, we enlarge the scale of the bounding box by 1.5 to capture more interactions between the object and the background. Next, we utilize the enlarged bounding box to crop the images, including the NOSS map, mask, and amdo mask. Secondly, we utilize Blender to render a portion of the synthetic dataset. In order to enhance the realism and alleviate the domain gap, we randomly select some real background images and replace the object background with them. After obtaining a high-quality synthetic dataset, we pre-train our network on it to enhance the precision of our results. This step furnishes a beneficial initialization for subsequent fine-tuning on real-world datasets. Despite the significant increase in dataset size achieved through the synthetic dataset, we further employ various data augmentation techniques to introduce additional randomness and variations. We employ the coarse dropout technique to simulate occluded or missing regions in the images. Additionally, we utilize Gaussian blur noise to fit the dynamic blurring of objects in the scene. Furthermore, we apply extensive color jittering to the images, altering their brightness, contrast, and saturation. These techniques help the model adapt better to various occlusion scenarios and the noise present in the real world. Our network architecture is illustrated as follows. Given an input image and a mask, we crop out the region of interest and predict intermediate features to directly regress the rotation and translation. We specifically choose a pre-trained convex as our backbone for this task. To facilitate the network's reasoning ability for occluded regions, we employ a generative adversarial model to enable a full adversarial process between the ground truth NOSs and the predicted NOSs. During training, our loss can be primarily divided into the geometric component and the GAN component. The GAN component is a straightforward generative adversarial loss, where the geometric component comprises an L1 loss with a penalty for NOSs, as well as losses for disentangled rotation and translation. For each unique instance, we train a model respectively. As shown in the figure, our model can accurately predict the 60 pose directly from RGB images, and the performance will on multiple object instances. In summary, we employed extensive data preprocessing and augmentation techniques, significantly enhancing the diversity and scale of our dataset. Furthermore, we propose a novel network called G2DIA and employ adversarial loss for training an effective NOS prediction network. G2DIA has shown excellent performance in occlusion scenarios. Thanks for watching.